Next speaker is joining us remotely for this presentation, Douglas Costa. He's going to talk about optionality as a binary operation. So thank you for joining us today.
Hello, everyone. Sorry not to be there in person, but I'm honored to be part of this memorial to Peter. I should mention that Peter and I first met in the mid-90s when we were both working as consultants for Susquehanna, and the head of quant research then was a student of mine who introduced us in Philadelphia. We had seen each other off and on sporadically at conferences, but the joint work I'm going to talk about today is our first collaboration. It began shortly after the pandemic started, when Peter called, knowing that I had a background in abstract algebra. And it was just incredible fun. I just want to join everyone in commenting on his amazing breadth of knowledge, but especially his joy in exploring ideas in mathematics, finance, and other areas. And I'm just sort of heartbroken that this is our first collaboration and that it will not continue. Okay, so let me try to share my screen. Okay. Okay, here we go. So optionality is a binary operation. This is joint work, as I said, with Peter, and it relates to abstract algebra. Peter loved to make connections between ideas and concepts of all kinds from multiple fields. And he also liked to make connections between people. And I have recently been thinking of him as being kind of like Paul Erdős. His brain was open to anyone who was interested in working with him. And now perhaps we each have a Carr number, similar to the Erdős number that mathematicians like to talk about. So this project explores the connections between option pricing and basic algebraic structures. It's partly inspired by Peter's work on a new kind of contract that he called stoptions. So if you're interested in following up, you should read that paper too. So in some ways, this talk will be a continuation of the talks by Federico and Pasquale from yesterday. They introduced a lot of these same notions, and Peter was obviously collaborating with them in this direction as well, and it was something fascinating to him. And I should mention that a student of his, J.P. Delevin, has also made some progress on these questions. Okay, so to start with zero rates and drift, as Federico and Pasquale observed yesterday, Peter had observed that a married put price in expectation looks like this. It's a expectation of the maximum of the strike and the future stock price. So here S is the current stock price, X is the absolute or gross return on the stock. That we're going to define to be a binary operation on the numbers K and S, in this case, the positive real numbers K and S. And I want to think of it as a function H of K and S, bivariate function. So notice it defines a binary operation, and notice looking at that expectation using elementary properties of expectation, that under reasonable assumptions about the continuity and support of the distribution underlying it, this function will be continuous in both coordinates, monotone increasing. 0 is a two-sided identity element. And the last observation is that it's homogeneous in K and S, which is a an analytical way of saying the algebraic property that ordinary multiplication of non-negative numbers distributes over this pseudo-sum. So there's a distributive law for multiplication over that circle plus, that pseudo-sum. Okay, so Peter liked to say that the married put function makes the interval from 0 to infinity a magma. In algebra, when you have a binary operation on a set and the set is closed under that binary operation, you call it a magma, but it has so little structure that the sense of magma is that it's kind of formless and void. If the operation is associative, that's a little bit more structure, and you call it a semigroup. If it has a two-sided identity element, then it becomes a monoid. If you go further and every element has an inverse, then it's a group, but we're not going to go that far. We'll be concerned with monoids. So if the underlying distribution is a conjugate power Dagum distribution, then the non-negative integers, real numbers, excuse me, form a monoid. And just the first line there is re-expressing what's called the conjugate power Dagum distribution with parameter b. And Peter had made this discovery that if you just calculate the value of the married put, it turns out to be this norm-like looking thing. K to the 1 over b plus s to the 1 over b, all raised to the b power. And just looking at that algebraically, it's patently associative, commutative, has zeros and identity elements. So this is a monoid. And now we can add that ordinary multiplication distributes over this sum. So it's almost like a ring. It's a semi-ring just because there are no additive inverses. There are multiplicative inverses, however, for the positive numbers. So that makes it actually what's called a semi-field. So it's a field except that there are no negatives. So this led Peter to say quite often that option pricing is just a change of arithmetic. In other words, when you're pricing a married put, and of course from the married put, you can get the put value easily and simply, and here we have options expressed in completely elementary terms. And if you think of the pseudo sum as the new arithmetic, then it's just adding two numbers. Okay, we can do a similar thing on the entire real line, but the extended real line, including minus infinity. So for a random variable defined on the entire real line, the zero mean logistic distribution with parameter b has the usual form, and Peter discovered, and we saw this pseudo sum yesterday as well, that the expectation value of the married put in the sense of the value, put on the value of some variable that could be positive or negative has this form. And algebraically, again, we see patently that this is associative commutative, and now negative infinity is the identity element, so it's a monoid, and in fact, ordinary addition now distributes over this pseudo sum, so it's again a semi-field. Now I want to bring in a critical result from analysis. Aczel in around 1949 showed that if in general you have a binary operation defined on an interval of real numbers, and it has the properties that it's continuous and monotone increasing in each coordinate, then it's associative if and only if it has a generator. In other words, a function, a monotone continuous function g from some other real interval j star onto j, and so that the pseudo sum is, excuse me here, is defined by g of g inverse of x plus g inverse of y. When we add to this that it's a monoid, so that there's an identity element, then it's a technical point here, but Aczel's theorem is more general, but when we add the identity element, then the J star is forced to be either the non-negative real numbers with 0 included, or the open interval minus infinity to infinity. So this G is then called a generator for the pseudo sum. This shows that the only associative operations on intervals of real numbers are just isomorphic transforms of ordinary addition versus via this isomorphism. So G, in algebraic terms, the generator is an isomorphism of monoids. And then we get a bonus when we've defined this pseudo sum. We can, if it's associative, we get a generator, and we can use the generator to then extend the product to a pseudo product by defining the pseudo product in terms of the generator. So we get this definition of the pseudo product. And the pseudo product distributes over the pseudo sum. So the interval J, which is mapped onto by G, becomes a semi-field isomorphic to either the 0 infinity interval or the minus infinity infinity interval. Okay, so just reminder, one of the consequences is that if you have a continuous order preserving associative operation, then it must be defined by a generator. And because it's defined by a generator, it must be commutative. And the identity element must be the image of 0 under G. So the first example was discussed yesterday. In this example of a generator, we choose the generator to be the Beeth power function. Then the pseudo sum is just the one that you get from the Dagum distribution. The pseudo product is ordinary multiplication, and this is the Dagum distribution-based married put semi-field. In example 2, which we also saw yesterday, we'll take the interval to be the extended real line extended to include minus infinity. Then J star is, again, I just want to point out that, again, J star is the non-negative real numbers. And now the generator function is the logarithm with respect to a base capital B. And then for all X and Y in J in this extended real line, the pseudo sum has that form of which Peter referred to as the log sum exponential. And this time the pseudo product turns into addition. So this is the logistic distribution based married put semi-field. So this corresponds exactly to computing married puts under the logistic distribution. So when Peter discovered these things, he was super excited. He was seeing connections between option pricing and algebraic structures, and he raised these questions. What are the possible algebraic structures on intervals of real numbers which are defined by married puts or other contracts? What are the distributions that are possible given properties of pseudo-arithmetics which could represent married puts, and which distributions on what intervals correspond to what algebraic structures? So open-ended questions. And the question that he posed to me was, can we find all intervals J with a distribution and on them, which makes married puts define an associative operation? Now, this raises a key philosophical question, which Peter started referring to as the associativity problem. So why does associativity in particular matter? And there are possible answers. You can talk about computational efficiency. If you think of his stoptions, they turn out to be sort of iterated married puts, and you can value them in the Dagum case by taking iterated Dagum pseudo sums, but you have to do it from maturity backwards in time and associate them in that order. But if it's associative, then it doesn't matter how you put the parentheses around the pseudo sums. And this could be relevant if you were to say, contemplate something like resettable and extendable stoptions, that where the holder of the stoption has the option at any time to extend it with an added floor or two. Okay, but that's still kind of a, I would categorize that as an important philosophical question related to this. Okay, so answers part one. So during the pandemic, I had lots of fun. Maybe that's most of the fun I had during the pandemic, trying to answer these questions. And through our discussions, I was able to show two results. The first one is that if you look at the extended real line, the whole real line, and you define the pseudo sum as the married put in the sense of expectation of maximum of x and y plus bz, where z is a standardized random variable, then that is an associative operation if and only if z is standard logistic. And on the non-negative real numbers, if you define the pseudo sum as the usual married put function, that's associative if and only if z is a mean one conjugate powered Dagum random variable. Now, I think when we discussed this, Peter was kind of stunned and perhaps disappointed because I think he was thinking in terms of investigating a whole zoo of possible distributions and a whole zoo of different kinds of intervals, including finite intervals that might support this kind of representation as married puts or option prices. So here's the flavor of the proof in the logistic case. So in the logistic case, we had a parameter b, which is just going to represent the width of the logistic distribution. That's the L scale. But the first observation is it's easy to see that it suffices to handle the case b equals 1. And then I'm going to write the pseudo sum as this function of two variables h of x, y, express it as an integral, and assume associativity. Now, if you assume associativity, as a bonus, you get commutativity by the Aczel result. And so we use commutativity, which implies symmetry of z, the distribution of z. And then we use distributivity of addition over this pseudo sum to pull out the y in the middle, as you see in the third line there. And what that means is that associativity is equivalent to this functional relation on H, which is expressed here. Okay, so the next step is translating that statement into statements about options. So writing those as integrals or using put call parity, this statement turns out to be equivalent to the statement below. So let me highlight that. Well, that's not working. Okay, well, the last equation on that page shows the call. Now, in these formulas, the call as a function of a real variable just means the call with strike u. So call of u is the integral from u to infinity of z minus u f of z dz. Now, once we have this sort of bizarre looking relationship, which actually is equivalent to associativity of the married put operation, expressed in terms of these call functions, call as a function of strike. We know from Breeden-Litzenberger that by taking derivatives with respect to strike, we can translate that into a functional relationship on the survival function. And this involves a lot of calculations, which again invoke symmetry. But the result is this double star formula, which after lengthy calculation, you arrive at. And it looks kind of suggestive. So once you see this expression for the survival function of u plus v, expressed in terms of the survival function of u and the survival function of v, just define a function f to be 1 over the survival function and then -1. And inverting both sides of double star, you get the functional relation on f that f of u plus v is f of u times f of v, which we recognize as being a functional equation for an exponential. So we get the conclusion that f of z is exponential, and then solving for the survival function, z is standard logistic. So that's the flavor of the proof. An analogous proof for the Dagum case on the non-negative real numbers. Okay. Now, for something a little bit more subtle, Aczel, we can invoke Aczel, and we can realize that since all these associative operations are defined by generators, it doesn't matter which associative operation we use as the base case. So we can use the logistic pseudo-sum as our base case and define all the other associative operations isomorphic to the 0 to infinity case through that. And then we can ask the question, can we find all of the generators for which married puts using the new arithmetic, the pseudo arithmetic of the new semifield with the pseudo product and the pseudo sum? So those are the things down here. We can ask, given a generator, or what are all the generators for which there actually exist distributions W, random variables W, for which this pseudo product defined by the generator is the expectation of a married put in this sense. And for decreasing generators, we have to replace the max by the min, and then they become covered calls. And the answers are pretty limited. It's just functions of the form a e to the mx plus b, or just linear functions, ax plus b. And the distributions that result are also very limited. If m is positive, then w has to basically be a conjugate power Dagum. If m is negative, it's got to be a sigma dala, which is just a reciprocal of a conjugate power Dagum random variable. And if it's linear, then it's logistic. So we've determined all the distributions under which married puts or by rights, covered calls, defined with respect to the pseudo arithmetic, create associative binary operations. We've seen that associativity is surprisingly restrictive, and we can determine all the pseudo arithmetics which can be realized as married puts or by rights in this way. Now, I just want to point out all these things we've done have been for the case where J star, the base interval, is the non-negative reals, and we haven't done anything with the other possible case for developing a monoid, which is the real line with 0 in the middle as the identity element. And it just seems to be hard to think of derivative contracts that would define well-behaved operations on that in that case. So Peter had hoped to find a wide variety of distributions and intervals with those distributions that could create monoids, and he was somewhat disconcerted to find associativity was so rigid and limiting. But looking deeper, I think things are more interesting. Binary operations defined by married puts in general, we can conclude are mostly non-associative and non-commutative. So they're defining algebras in which the distributive law holds for multiplication over addition, and multiplication is commutative and has inverses, but addition itself is non-associative and non-commutative. So what can we say about such structures? And what relations are there among underlying distributions which correspond to isomorphism classes of these structures? So just to conclude, let's note the strange case of Black-Scholes. So it was mentioned yesterday, I think, in Federico's talk that you can simply, with zero rates and drift, you can write the Black-Scholes married put operation in this form. So here it is. And it's clearly commutative by the symmetry in that expression. But we know, since the underlying distribution is log normal and not conjugate power Dagum, that it can't be associative. So that's interesting. And that leads, this is just an example. We can ask if we apply a generator to that operation, can we realize it as a married put value? Well, the answer is yes. If you use the log generator to map onto the entire real line, then the answer is yes. And the machinery we've developed shows that the distribution has this cumulative distribution function, replacing, say, the logistic. If we used capital H here as logistic, we would get an associative operation, but using this one, we get the non-associative operation on minus infinity to infinity that is isomorphic to the Black-Scholes binary operation on the positive real line. So interesting. So basically, that is it.
Thank you very much. Any questions here in the audience? Yes.
Hello, hi. I have a question, more a curiosity. So another place, I guess, where this Aczel theorem kicks in is the construction of Archimedean copulas, for instance. I think they have some similar construction. So I was wondering if we can find a connection between maybe married put and Archimedean copula, if there is any interpretation of, looked into it.
I haven't. Interesting question.
Yeah, sure. That's thank you.
Hi, Dag. It's Federico here. I wanted personally thank you for the talk, because like it's been a while since I haven't seen like pseudo sums and algebraic structure applied to finance in the way Peter did. And I just wanted, it is not really a question. It's more like an observation that I think it's very interesting. I think how once you move away from the standard way of thinking about options in finance and you move to this abstract algebraic way, it seems that Black-Scholes becomes to some extent accidental, I would say, like, because it's not the most natural way of working with options. And I think it's what you showed in the slide about the pseudo sums and the pseudo product, I think is extremely, at least for me, I think it just is extremely beautiful, because pseudo sums essentially are option prices and pseudo products are total returns, or at least this is how I like the multiplication in the conjugate power Dagum that works with only mean one and parameter b are essentially price ratios. So the product the pseudo product is still a product, and therefore the total return. So I was wondering whether you are or might potentially be interested in developing sort of an iterative, like, because at this point we had just two variables in a sense, and sort of going back to the idea of the stoptions, but more also on the conjugate side of the story, which I think I don't know if Peter had developed something, but like in terms of compounding this n times, because I think since I believe this is a more natural way of looking at options, I think this is also a more promising way of looking at American options.
Mm-hmm. Yeah, he had hoped to apply this to American options as well. So yeah, he definitely was thinking along those lines. And I would add, by the way, that I think he would have been happy that to think about, I mean, and we didn't get a chance to discuss this before he passed, but that last remark in the slide about how you can develop new distributions by just applying generators to married put fund and see what you get. It can be a little tricky. They don't all turn out to be valid distributions, but when they do, you could get interesting things, and he would have been intrigued by that to pursue that further, I think.
Thank you so much again.
Thank you.